Hi, I'm Professor Piggy, and today we will talk about processors. Yep, we are going to pull back the curtain on the single most important component inside every single one of your devices, whether it's your phone, your laptop, or your big gaming PC. So have you ever opened up your system information, to see what's under the hood, and you're just hit with this wall of letters and numbers, and you feel completely overwhelmed? Yeah, don't worry, you are definitely not alone in that. These technical terms, right? They get thrown around all the time in marketing and on spec sheets. It can feel like you're trying to learn a whole new language. But what do they actually mean for you, for how your device actually performs? Well, that's exactly what we're going to do today. We are going to demystify the CPU, the central processing unit. I want you to think of it as the brain of your computer, and by the end of this, you'll be able to speak its language no problem. Okay, let's dive right in. Before we talk about what a processor does, let's just take a look at what it actually is, as a physical thing you can hold in your hand. At its most basic level, a CPU's job is to do math, a whole lot of it, and incredibly fast. It's this amazing little chip that's packed with, and this is not an exaggeration, billions of microscopic transistors. Its entire purpose is to process these massive strings of ones and zeros, that's binary, the language of computers, to carry out every single command you give it. Now, this powerful little brain needs a way to connect to the rest of the computer, to the motherboard. And in the modern world, the two big players, Intel and AMD, do this in two different ways that are basically mirror images of each other. Okay, so you've got LGA, Land Grid Array, which is Intel's go-to. The pins are on the motherboard socket, and the CPU itself is flat. Then there's PGA, Pin Grid Array, which is common for AMD. Here, the delicate pins are on the processor itself. It's a really critical physical difference, and it's one of the first things you have to think about if you're ever building a PC. All right, so now we know how it plugs in. Let's talk about the actual language the processor speaks, and this all comes down to its fundamental architecture. You have almost certainly seen these terms before, 32-bit and 64-bit. The difference between them is really all about how much data the CPU can grab and work with at any one time. It's like asking, is the highway for information between the CPU and your memory a 2-lane road, or is it a massive 64-lane superhighway? And get this number really puts that difference into perspective. A 32-bit CPU is limited. It can only talk to about 4 gigabytes of memory, of RAM. That's it. A 64-bit CPU, on the other hand, can theoretically address over 17 billion gigabytes. Now, of course, no computer has that much RAM today, but it just goes to show you how 64-bit architecture completely blew the doors open for the powerful systems we all use. So here's the crucial part. This isn't just some abstract number. It has very real-world consequences for you. You need 64-bit drivers for your hardware to work on a 64-bit system. And hey, have you ever wondered why Windows has 2 Program Files folders? This is why. That x86 folder is basically a legacy container for all your older 32-bit apps, keeping them separate from your modern 64-bit ones. Okay, so let's dig a little deeper. Now we're going to explore the two major design philosophies that determine how a processor actually gets its work done. These are two totally different approaches to solving the same kinds of problems. Think of it like a math problem. If I ask you to figure out what 7 times 7 is, you could do it in one complex step, multiplication. That's kind of like CISC. Or you could do it in a bunch of really simple steps. 7 plus 7 plus 7 plus 7. You get the idea. That's RISC. Both ways get you to 49, but the process is completely different. So CISC stands for Complex Instruction Set Computer. This is the traditional architecture for what we think of as computers, desktops, laptops, servers. It's designed to handle a huge variety of complex tasks using powerful, single instructions. This is the world of Intel and AMD. And on the other side, you have RISC, which stands for Reduced Instruction Set Computer. It uses a much smaller set of very simple instructions, but it executes them incredibly fast. The most famous example here is ARM. And this architecture's amazing power efficiency is the whole reason it's in virtually every single smartphone and tablet. It's how you get incredible performance without your battery dying in an hour. Now, let's zoom in even further inside the chip. See, a modern CPU isn't just one single brain anymore. For the last couple of decades, the way we've made computers faster hasn't been just about raw speed. It's been about adding more brains into a single package. You see, instead of trying to make one core go faster and faster, which started running into serious problems with heat and power consumption, designers just started adding more cores. Each core is basically its own little independent processor, which allows your computer to genuinely multitask, to work on different things at the exact same time. But wait, it gets even more clever. Intel came up with this really neat trick called hyperthreading. What this does is it allows a single physical core to handle two separate instruction streams, or threads, at the same time. It essentially fools your operating system into seeing two processors where there's only one, which massively cuts down on wasted time and makes everything feel snappier. And this table is a perfect example of how it all comes together in a modern chip. These Intel CPUs use a hybrid design. They have powerful P cores, or performance cores, for the really heavy lifting, and these support hyperthreading. And then they have smaller, power-saving E cores, or efficient cores, for background tasks. So if you look at that i5, it has 6 P cores, which means 12 threads, plus 8 E cores, for a total of 20 threads. It's this complex balancing act that delivers that amazing high-end performance. So, okay, we've got all these complicated parts, right? We have architecture, cores, threads, these different design philosophies. So how do we actually measure what a processor is capable of? Well, clock speed is the classic metric everyone talks about. It's measured in gigahertz, and it's basically how many billions of calculations a CPU can run per second. But that's only part of the story. The number of cores and threads tells you how good it is at multitasking. And then you have other key features like virtualization support, which is critical if you want to do advanced stuff like run another operating system inside a virtual machine. True performance is really a combination of all these things. And this is probably the most important thing to take away from all this. You can't just look at one number and know if a CPU is good. It's a finely tuned system. A processor with a lower clock speed but way more cores might be an absolute beast for video editing, while another one with a super fast single-core speed might be better for certain types of games. Understanding how these elements work together helps you finally decode those specs and know what's really powering your devices. And that really leaves us with a fascinating question for the future, doesn't it? As our demands for both power and efficiency just keep growing, and as these designs get even more complex, integrating specialized chips for things like on-device AI, what new possibilities are going to be unlocked? The brain of our digital world isn't just getting faster anymore, it's fundamentally changing how it thinks.